So in this video, I'll discuss diastereomers. So diastereomers are a type of stereoisomer, and stereoisomers simply indicate that the molecules have atoms that are connected the same, but their arrangements are different. And so with diastereomers, they're not going to be perfect mirror images, however, they are stereoisomers. So for instance, if we have the following compound. So let's just say we have OH, and we have a CH3. And so this is a Fisher projection that allows you to see horizontal and vertical lines. So it still gives you information about the three-dimensional arrangement without actually showing solid wedges or dashed wedges. It just makes it easier to draw and quicker to draw that molecule. And so with this, in order to determine whether or not you have a diastereomer, or you can even have an enantiomer, you have to make sure that you're dealing with stereoisomers. And so stereoisomers means that around each chiral center, that molecule, when we're comparing them, each molecule is going to have the same 4 groups. So by groups, we're simply saying if we start at that particular carbon and work our way to the end of the molecule in all 4 directions, it's going to be the exact same. So looking at that top carbon, to the left we have a hydrogen, above we have a methyl, to the right we have a hydroxyl, so that OH group, and down below we have this CH-OH-CH3. So 4 different groups. So in order for it to be a stereoisomer, the other molecule has to have the same arrangement, or the same connectivity, not arrangement, excuse me. So that means we have to have the same 4 groups. So this carbon has to have that methyl group, it has to have a hydrogen, it has to have the OH group, and it has to have a CH-OH-CH3. And so this one has the same 4 groups. So we have the hydrogen group, we have the methyl group, we have the hydroxyl group, and then we have our CH-OH-CH3 group. So these molecules both have the same 4 groups. However, if you notice, the arrangement is different. For the molecule on the left, so if I were to redraw it without circling anything, if I were to put a mirror up to this molecule, what I would see would be the mirror image. The mirror image would basically be its reflection. With that reflection, what's on the vertical is still going to be in that same position. So when you look in the mirror, things that are pointing up are still going to be pointing up. Things that are pointing down are still going to be pointing down. But what changes are things that were pointing horizontally. So instead of this OH being to the right, the mirror image would have it to the left. Therefore, the hydrogen would be to the right. These 2 molecules contain 2 chiral centers, and around each chiral center, we see that they have now swapped. So they are the exact opposite. When all of your chiral centers are the exact opposite, the molecules represent enantiomers. Enantiomers are perfect mirror images. So in other words, all chiral centers change. However, that's not always the case. We don't always have it where every chiral center that's present changes. We could have had a molecule, the very first pair that I drew up top, I have the CH3, then I swapped the OH and the H around that top carbon. The bottom carbon was still the same. So we still have 2 chiral centers, but around those 2 chiral centers, only one has swapped. So if we notice here, this one changed, because those were the only 2 chiral centers. it represented enantiomers. But now, this one changed, but this one did not. So not every chiral center changed. In this case, they're going to represent diastereomers. And technically, these are epimers. So epimers are molecules. They are special types of diastereomers. But this type of diastereomer, only one chiral center changes. So epimers are diastereomers. Only one chiral center changes. If we had an example that had more than two chiral centers, it would be easier to see. But an epimer is technically a special type of diastereomer where only one chiral center changes. Diastereomers are not perfect mirror images. So in other words, not all chiral centers change. So in this case, we had two chiral centers, only one changed. So therefore, it was a diastereomer. More specifically, because only one changed, we can really refer to it as an epimer. So let's look at one that has more than just two chiral centers. May make it a little easier to understand how to distinguish between the diastereomer and the epimer. So I thought about doing a carbohydrate, but I'm going to just do a regular compound. And so with this compound, we have 1, 2, 3, 4, 5, 6 carbon atoms. Carbons 1 and 6 are not chiral because carbon 1 has 2 hydrogen. We can't have more than one of the same group. Carbon 6 has 3 hydrogen. So that means that carbons 2, 3, 4, and 5 are going to be our chiral centers. We can look at each. We can see that carbon 2 has the hydrogen to the left, the CH2OH to the right, the OH to the right as well. CH2OH above and the OH to the right, and then all of this down below. Carbon 3 has the hydrogen to the left, all of this above, the OH to the right, all of that below. Carbon 4 has the OH to the left, all of that above, the hydrogen to the right, and then this below. Carbon 5, hydrogen to the left, all of that above, chlorine to the right, methyl to the right. Methyl down below. So 4 different groups. So carbons 2, 3, 4, and 5 are all chiral centers. The mirror image, so there's only one way we can get a perfect mirror image or a true mirror image. Again, what's on the horizontal changes, but what's on the vertical remains the same. So that CH2OH and that CH3, they're going to remain the same. But for the perfect mirror image, everything that was on the right will now be on the left. Everything that was on the left will now be on the right. This is a perfect mirror image. This chiral center changed. This one, that one, and that one. All 4 chiral centers changed, so therefore this would be your enantiomer. What if I had given this one? So comparing this, so this is going to be what I'm going to call the original. Comparing my original, if I look at carbon 2, OH was to the right, it's still to the right, so it did not change. Carbon 3, OH was to the right, now it's to the left, so it did change. Carbon 4, the OH was to the left, it's still to the left, so it did not change. Carbon 5, the Cl was to the right, now it's to the left, so it did change. So not every chiral center changed, so it cannot be an enantiomer. However, since it's not a perfect mirror image, it's a diastereomer. So diastereomer. So enantiomer, all chiral centers change. Diastereomer, not all will change. And then the last one we talked about was an epimer. Now there are different ways that you can have diastereomers, because I can have other arrangements as well. But the key is that not all of the chiral centers will be different. So let's just say I have this compound. So again, comparing it to my original, carbon 2, the OH was to the right, now it's to the left, so that changed. Carbon 3, the OH was to the left, was to the right, it's still to the right, so that didn't change. Carbon 4, the OH was to the left, still to the left, that didn't change. Carbon 5, the chlorine was to the right, it's still to the right, that didn't change. Only one change. So although it is a diastereomer, because not all change, this would specifically represent an epimer. So it's a special type of diastereomer where only one changes. So an epimer is a diastereomer where only one chiral center changes. And so when you're trying to determine the relationship between compounds, you want to look at the chiral centers and compare whether or not all chiral centers changed, whether or not one changed, or whether or not more than one but less than all. So one little trick that I tend to show, if you just think about numbering and ordering things, we have one, all the way down here we have all, and then of course here would be somewhere in between. So if only one changes, it's an epimer. If all change, it's an enantiomer. Anywhere in between this would represent a diastereomer. And this is referring to your chiral centers. Now I should say changes around the chiral centers. So I hope this helps. If not, feel free to let me know. Thank you.